Okay, let us start with the new topic, photoelectric equation. Uh, this concept was given by Einstein. According to him, we consider a metal surface. This is a metal surface. So when electromagnetic radiation of some energy is incident on the metallic surface, when some electromagnetic radiation of some energy E is incident on the metallic surface, some amount of energy is absorbed by the metal surface called work function, denoted by phi, and after absorption of some energy the metal surface ejects some electron away with some energy, kinetic energy. So here the incident energy is denoted by E. Incident energy is equal to E. This is the energy of radiation being incident on the metal surface, and the metal surface absorbs some energy called work function to emit the electrons, and the emitted electrons will have some energy, that is kinetic energy. Emitted electrons is equal to kinetic energy. So from the principle of conservation of energy, the incident energy must be equal to the sum of the energy absorbed by the metal surface and the kinetic energy with which the emitted electrons are ejected from the metal surface. If F be the frequency of radiation being incident on the metal surface, then the incident energy is equal to HF. Similarly, if lambda is the wavelength of electromagnetic radiation incident on the metal surface, then the incident energy can be written as hc by lambda. Similarly, if the emitted electrons are emitted with velocity v, then the kinetic energy of the emitted electrons is equal to half mv square. Work function is the energy absorbed by the metal surface to emit the electrons. So the minimum energy work function can be defined as the minimum energy required by the metal surface to emit the electrons or to release the electrons from its surface. So this work function is denoted as hf naught or hc by lambda naught, where f naught is the threshold frequency and lambda naught is the threshold wavelength. They denotes the boundary of the values at which the metal surface is able to eject electron. So with these values, the equation 1 can be further written as hf is equal to hf naught plus half mv square, or hc by lambda is equal to hc by lambda naught plus half mv square. The emitted electrons from the metal surface are called photoelectrons. And the current produced due to these photoelectrons is called photoelectricity. Now if some opposite potential is applied to the photoelectrons to stop its motion, to keys its motion, then the potential that can stop the motion of photoelectrons is given by EVS is equal to half mv square, where V is the potential that opposing potential that will be required to stop the photoelectrons, to stop the motion of the photoelectrons. Since this potential stops the motion of the electron, it is called stopping potential and denoted by EVS. So equation 2 can again be termed as Sc by lambda is equal to Sc by lambda naught plus EVS. Now let us start with the numerical related to this topic. Electrons with maximum kinetic energy of 3 electron volt. Kinetic energy is equal to 3 electron volt, which is equal to 3 into 10 power 3 into 1.6 into 10 power minus 19 joule, and the electromagnetic radiation has wavelength 1.5 into 10 power minus 7 meter. Now we need to determine the work function is equal to what, threshold wavelength is equal to what, and the stopping potential Bs is equal to what. We can use our formula. First we calculate the incident energy. E is equal to Sc by lambda, which is 6.62 into 10 power minus 34 into 3 into 10 power 8 by 1.5 into 10 power minus 7. This gives 1.324 into 10 power minus 18 joule, which is equal to 8.275 electron volt. So now then we have electric incident energy. E is equal to work function plus kinetic energy. Now let us put the values. 8.275 is equal to 5 plus 3 electron volt. Therefore 5 comes to be 5.275 electron volt. Now we get the first answer. Now for the second answer, again work function is equal to Sc by lambda naught. For this we need work function in joule, so 5.275 into 1.6 into 10 power minus 19 joule. So putting these values, 5.275 into 1.6 into 10 power minus 19 is equal to 6.62, 10 power minus 34 into 3 into 10 power 8 by lambda naught. Solving this we get lambda naught is equal to 2.35 into 10 power minus 7 meter. This one is the second answer. First answer for the work function, second answer for the threshold wavelength, and last requirement is stopping potential. So EBS is equal to kinetic energy, or 1.6 into 10 power minus 19 into Bs is equal to 3 electron volt. In joule it can written as into 1.6 into 10 power minus 19. Therefore Bs is equal to 3 volt. We got the answer. So next question, a retarding potential difference of 3.38 volt is required to stop the emission of electron from a potassium surface by ultraviolet radiation of wavelength 2000 angstrom. Calculate the photoelectric threshold wavelength for potassium surface. So here given potential difference required to stop the electron is equal to 3.38 volt, and the incident radiation as the wavelength of lambda is equal to 2000 angstrom. This is equal to 2000 into 10 power minus 10 meter. We need to calculate the photoelectric threshold wavelength. Lambda naught is equal to what? So from lambda we will calculate the incident energy. Sc by lambda is equal to 6.62 into 10 power minus 34 into 3 into 10 power 8 divided by 2000 into 10 power minus 10. This comes to be 9.93 into 10 power minus 19 joule. Now we will use the photoelectric equation. E is equal to 5 plus kinetic energy, or E is equal to hc by lambda naught. We will put this formula for work function, and kinetic energy we can write EBS. Now putting the required values, 9.93 into 10 power minus 19 is equal to 6.62 into 10 power minus 34 into 3 into 10 power 8 by lambda naught is to be required to be calculated, and E 1.6 into 10 power minus 19, BS 3.38. Substituting all these values, we get lambda naught is equal to 4.41 into 10 power minus 7 meter, which is the required answer. So we have a next question. A photoelectron from cesium surface has kinetic energy of 4.0 into 10 power minus 19 joule. The work function of cesium is 1.8 electron volt. What is the maximum wavelength of light which could have ejected this electron? So the maximum wavelength of light that can eject electron is the wavelength of incident energy. So we need to calculate the value for this numerical. We will convert the work function into joule. 1.8 into 1.6 into 10 power minus 19 joule. Now we will use the photoelectric equation. E is equal to 5 plus kinetic energy. E can be written as hc by lambda. The value of phi is 1.8 into 1.6 into 10 power minus 19, and kinetic energy is 4 into 10 power minus 19. Substituting the value, 6.62 into 10 power minus 34 into 3 into 10 power 8 by lambda is equal to 1.8 into 1.6 into 10 power minus 19 plus 4 into 10 power minus 19. Solving this, we get lambda is obtained as 2.89 into 10 power minus 7 meter, which is the required answer. So here is the next question. When light of frequency 5.4 into 10 power 14 hertz, 5.4 into 10 power 14 hertz is shown onto a metal surface, the maximum energy of electron emitted is 1.2 into minus 19 joule. If the same surface is illuminated with light of frequency 6.6 into 10 power 14 hertz, the maximum energy of the electron emitted is 2 into 10 power minus 19 joule. So this question is, and calculate the value of Planck's constant lambda is equal to what? So this question says if the incident frequency of radiation is 5.4 into 10 power 14 hertz, then the kinetic energy of electron emitted is 1.2 into 10 power minus 19 joule. If the frequency becomes 6.6 into 10 power minus 14, then the kinetic energy of the emitted electron will be 2.0 into 10 power minus 19. So this is the question of two conditions. So we will apply two different equations for both the condition. For first condition, the photoelectric equation is E1 is equal to phi plus kinetic energy 1, or HF1 is equal to phi plus kinetic energy 1. This is the first equation. And similarly for the second condition, the equation can be written as E2 is equal to phi plus kinetic energy 2, or HF2 is equal to phi plus kinetic energy 2. in both the equations phi is common because the surface, illuminating surface, metal surface is same in both the conditions. Now we will solve these two equations. From equation 1 gives phi as hf1 minus kinetic energy 1, and equation 2 gives phi as hf2 minus kinetic energy 2. And since phi is both same in both the cases, then we can write hf1 minus ke1 is equal to hf2 minus ke2, or hf2 minus hf1 can be written as ke2 minus ke1, or we need to calculate the Planck constant, so this comes to be ke2 minus ke1 by f2 minus f1. Now we will put the values. Kinetic energy 2 is 2.0 into 10 power minus 19. Kinetic energy 1 is 1.2 into 10 power minus 19. And putting the values of frequencies, f2 is 6.6 into 10 power 14 minus 5.4 into 10 power 14. So solving this, we get 6.67 into 10 power minus 13, 34 joules second, which is the required answer. Now next question, if the wavelength of incident light is reduced from 400 nanometer to 360 nanometer, there is a change in stopping potential of 0.34 volt. Find the value of Planck's constant. So here the question is, now the first incident for the first wavelength of incident light was lambda 1 is equal to 400 nanometer. This is equal to 400 into 10 power minus 9 meter. Now we consider that the stopping potential for this incident wavelength is V1. Similarly, when the wavelength becomes 300, incident wavelength becomes 360 nanometer, or 360 into 10 power minus 9 meter, then we consider the stopping potential as V2. Now according to question, the stopping potential, the change in stopping potential is equal to 0.34 volt, and we need to calculate the Planck's constant is equal to what. Now we will again write photoelectric equation for first and second condition. For first condition, we can write E is equal to 5 plus kinetic energy, or h c by lambda is equal to 5 plus EBS, or for first condition, SC by lambda 1 is equal to EB1, or phi is equal to ESC by lambda 1 minus EB1. This is equation 1. Similarly, for the second case, can be written as phi is equal to SC by lambda 2 minus EB2. Phi is same in both the cases because the metal surface is considered to be same. So equating equation 1 and 2, we get SC by lambda 1 minus EB1 is equal to SC by lambda 2 minus EB2, or EB2 minus EB1 is equal to SC by lambda 2 minus SC by lambda 1, or B2 minus B1 is equal to 1 by E SC by E 1 by lambda 2 minus 1 by lambda 1. Now we will put these values to get the value of Planck's constant as 0.34 is equal to h into 3 into 10 power 8 by 1.6 into 10 power minus 19, 1 by 360 into 10 power minus 9 minus 1 by 400 into 10 power minus 9. Solving these equations, we get the value of H as 6.5 into 10 power minus 34 joule second, which is the required answer.